Hey, what's up folks? Mr. Foreman here, going to record a quick video talking about how to solve a beam deflection problem start to finish. Hopefully this is a helpful resource for you. So we're going to be looking at the simplest case, a beam that is supported at both ends, and we're going to read it, and we're going to draw it, and then we're going to solve it. So in this one, a 2-inch by 2-inch steel bar spans a 3-foot long gap. A 250-pound construction worker stands on the center of the bar. How far will it deflect? First thing we're going to do is draw a profile sketch, in other words, like a side view. What does it look like? So we know it is supported at both ends. Let's make that triangle a little better. So we're going to draw it like this, little triangles. Those are our little supports, our little base. If I were being less lazy, I would hold my pen to make it snap, to make it straight lines, but this is fine too. So all these little things I'm drawing kind of help me know what I'm showing. You know, these little hatches here show me this is the ground. These little triangles shows me these are pin supports. And then I know this beam is a beam. So by adding those little things, it's actually showing me extra information that I know beyond just drawing the beam. And it's all going to come into play. I'm now going to annotate that drawing. So I'm going to look at the fact that it tells me it's a 3-foot long gap. So I'm going to write L equals 3. I'm going to draw that here. I know I'm using L, by the way, because I've got my PLTW formula sheet over here. I know I'm switching a lot in this video, and I will go to the beam deflection down here. And I know I'm looking at this case where we have the two supported ends, and I know I'm going to care about eventually this equation. So PL cubed of 40 ADI. So L is the length of it. That's what I'm referencing here. So back to the situation. A 215-pound there, construction worker. So that is the P is the letter we're going to use for a point load, stands in the center. So I'm going to label that there. P is 215 pounds. I'll make the L 3 feet. I'll give it a little single tick mark to show that it's feet because that's going to matter eventually. And the question is, how far will it deflect? In other words, what is our delta? Or let me see. Let me remind myself. We use capital delta here in PLTW, so I'll use a capital delta. Some sources use a lowercase delta, but I'll try to be consistent. So I will undo that delta and make it a capital delta. That's what we want to know. Now, the one piece of information we haven't used yet here is, of course, the cross-section of the steel bar. That's because we can't draw this, right? In a side view, we're going to have to draw the cross-section as well. So this is, again, as if I had my eyeball over to the right over here, and I were looking at the side of the bar. This is what I'm going to see. That's what I'm drawing when I draw a cross-section. So I'll erase that. And this is simple. It is a square. It tells us it's 2-inch by 2-inch. We know it's a square. And I'll label my sides. It's always good to annotate, both for you, for your brain, and for me as a teacher. If you annotate, I know that you know what you're supposed to know. So our cross-section is a square, 2-inch by 2-inch. Fantastic. So the first thing we're going to do is find the IXX, because this, remember, is based on the geometry of it, kind of like that thickness of it. It doesn't matter what the material is, it matters what the geometry is of that cross-section. So I'll remind myself, I'll look at the PLTW formula sheet. I will go up a section to the section properties. Now, the only one they give us is a rectangle. For anything else, like an I-beam or a semicircle or a hollow rectangle, we're going to have to look those up in other places or use those in other places. But we have the rectangle, which is BH cubed over 12 is the IXX. So I'll write that down for myself. IXX equals BH cubed over 12. Always helps to show it all out, because then, this one's pretty simple, the base is 2 inches, the height is also 2 inches cubed, all over 12. This one I'm going to do in my calculator. I'll show all the work. I will use this alpha frac to get a fraction, just so we can really see. 2 times 2 to the third, all over 12. Be aware, it's only the second 2 that is being cubed. This is not 4 to the third. I'm not multiplying the 2's. Only the height, the second 2, is to the third power. Solve that. That is 1 1/3. I like decimals a lot of the time for this, so that is 1.3, repeating, of course. So that is 1.3 and I'll do another one. Inches to the fourth is the IXX. So this is that number that describes the geometry of this beam and its resistance to deflection. We also need to know, and I'll remind us, about the material and its resistance to deflection. If we go back and look back at this deflection equation, right, the delta PL cubed over 48 EI. P is that point load, that weight of the construction worker. L, the length of it, we've got that. The 48 is just a constant. The I, we just found the IXX. But the E, the modulus of elasticity, or the Young's modulus, that's a property of the material. Sometimes I'll give that to you, but sometimes you'll have to look it up. Now, in reality, we would want to really know what kind of steel this is. You know, all I say here is steel. We don't know what hardness, what carbon content, stainless, high carbon, low carbon. You know, there's a lot of things this could be. But this is problem solving. So we're going to estimate. We're going to guess. I'm just going to open a Safari browser, and we'll just use the old Google machine this time. You know, I'm going to give you access to other links and other resources maybe later. We're just going to Google this right now. Steel modulus of elasticity, and it's there. It's a second autofill. Click that. Now, I'm not going to trust that AI overview. AI is not good. It could be good, but it's not good. So we're going to go in this engineering toolbox. This is one good source for common things. We're going to let's find some. I don't know how they have it listed in this one. Let's look down for steel. Steel, yeah, high strength alloy, stainless, structural. We'll say this structural. Why not? So the Young's modulus here is 200 gigapascals, but I'm actually going to tap this and change it to, I hope, PSI. There we go. Because we're doing everything in inches and pounds right now. So back to the steel, 29 PSI. See there, that 29 PSI. And that is GPSI, or MPSI, mega pounds per square inch. In other words, millions of pounds per square inch. So I'm going to write that down before I get. E is 29 times 10 to the 6 PSI. So times 10 to the 6 there, that's scientific notation for million. If you forgot, believe it or not, that is also in the formula sheet way up here, way in section 8 here. Prefixes, numbers greater than 1. Mega right here, capital M, is 1 million, is 10 to the 6. So you don't have to have these memorized. We will give them to you. This is something you can Google. It's something you can research. So now that we've got that out of the way, let's go back to the problem again. Now, believe it or not, we can finally start. So the deflection calculation, let's go back to the formula sheet. See, a lot of back and forth. We got to have a lot of tabs open. We got to have our brain working. Back here. So it is, again, this beam supported at both ends with a point load. That's what we're talking about. Here is the deflection formula. You know what? We're going to test something. Don't know if this is going to work. It would make our life easier if it does. I'm going to copy this as an image. I'll see if I can open it to another Notability. If so, let's see. Oh, I can. Look how easy that makes my life. That's fantastic. There you go. Life hack. We just learned it together. Then I can plug in, and it's just plug and chug. P, 215. L, 3. All over 48. E, 29 times 10 to the 6th. I, 1.33. Things to notice. Oh my gosh, I almost made a mistake. I wonder if my viewers at home know what my mistake was. I'll let you think about it for a second. Here it is. My IXX, inches to the 4th. My modulus of elasticity, pounds per square inch. Inches. My length is in feet. So maybe you were yelling at your computer saying, oh, Schwarman, we got to make that feet. You're right. So the L is 36 inches because 3 feet times 12 inches per foot. Here, and I'll even show you what I'm doing here. 3 feet times 12 inches per foot. The feet cancel, we get 36 inches. So I'm going to fix this. All right, magic edit powers to the rescue. So when I first made this video, I made a mistake. I forgot to cube this. So I'm actually going to cube this, try and cut this into the video. Hopefully it's pretty natural, and we'll fix it. So anyway, the length is 36 inches cubed over 48 EI. The E we found, the I we know. I'm actually going to use the magic of the calculator to bring this back, and I'm just going to, whoa, hit the wrong button. And I'm going to, fat fingers, my fingers are so fat, I can't hit what I want. I'm going to bring this in, I'm going to arrow over. There we go. And raise that to the third power. So that, looking at that, everything looks good. Boom, boom, boom. 0.005 is our maximum deflection, 0.005 inches. And that is how you solve a beam deflection problem.